Hello everyone, welcome to Algebra 1 with Miss Betsy. I'm really glad that you're here with us again today. If you are tracking with me with your own particular textbook, this video is keyed directly to Algebra 1 for Christian Schools, published by Bob Jones University Press. This is the second edition. I'm on page 495, and this is section 12.5, entitled Adding Rational Expressions with Different Denominators. You don't have to be using the same text. This is how you're going to add rational expressions, regardless of what book you are using. But before we get started, I've got another lame riddle for you this morning, and I wonder if you can tell me what it is that is gray, has four wheels, and has a trunk. Well, that would be an elephant on roller skates. You can see that I already have things written on the board today. We're going to ignore what's behind me to my left right now and just look at this addition of fractions problem that I have here. This is just to get us into how we add rational expressions together. We learned that these are rational numbers because they're written in the form a over b, a numerator and a denominator, and the denominator has to be different from 0. So what we think of as just being rational numbers, you grew up, in your lower education calling those simply fractions. And then we had moved on in class to where we're talking about rational expressions, and that's where you can have a polynomial in the numerator, a polynomial in the denominator, excuse me, and the denominator of the polynomial can't have a value of 0. So we want to learn how it is that we're going to add rational expressions that have different denominators, and I want to show you and illustrate to you that it's very similar to the method in which you learned how to add together two fractions with different denominators. Now maybe way back in when you first began to work with fractions you thought, okay, 7 over 60 plus 11 over 90, that must equal 19 over 150. Because all you knew to do at that point was you just added numbers, and it was a big stretch to know that you added the numbers on the top. And since you added that, you must have to be supposed to add the numbers on the bottom, and you learned very quickly that was not what you had to do. But the denominators, these bottom numbers here, have to be the same. And you learned a variety of ways to make sure that you could rename these fractions with what we called a common denominator. And one method that you use to do this is by prime factoring each number to be able to find a method that will easily and a foolproof way of coming up with the correct common denominator here, which is going to be 180. So what you were taught to do is first you would prime factor each number. And if we prime factored 60, we would learn that 60 was equal to, and I'm going to copy it so that I don't misspeak, it's 2 squared times 3 times 5. 2 squared is 4, times 5 is 20, times 3 is 60. When you prime factor 90, you saw that 90, written as a product of primes, is 2 times 3 squared times 5, or 10 times 9, which is 90. And this is not a lecture on how you prime factor, so you can go back through my old videos or search anybody else's videos and they'll show you how to prime factor numbers, where you write them as a product of primes using exponents. And now you wanted to come up with what we call the LCM. It's the least common multiple, the lowest number that if you write a list of multiples, 60, of the numbers that you're trying to find a common multiple of, it's the very first time that you have the same number show up in each list of multiples. The way that you find the least common multiple of two numbers is you look at your list of, now where did my eraser go? You look at your list of prime factors, and you're going to write down every single unique prime number that is used as a factor. So we have 2 times 3 times 5. Well, obviously 30 is not a common multiple of 60 times 90, so we haven't completed doing our prime factoring, pulling those factors together properly. First we pick each prime number, and then we look at all of the numbers that we've factored here, and we use the largest exponent of any of those factors that appears. We have 2 to the first, 2 squared, so our least common multiple is 2 squared. We have 3 squared here, 2 squared times 3 squared times 5. 2 squared is 4, times 5 is 20, times 3 squared, which is 9. 20 times 9 is 180, which is what I mentioned just a moment ago was going to be the least common multiple of 60 and 90, and I even showed it to you writing these numbers out here. Now, this is a method that some of you have used when you were working to find common denominators with rational numbers here. Some of you didn't, but I want to show you this way because it directly relates to finding the common denominator of rational expressions. What we're going to do now is rewrite our original problem, but we're going to write the denominators as in their factored form. So this would be 7 over 2 squared times 3 times 5 plus, let me space this out, plus 11 over 2 times 3 squared times 5. And at this point I'm going to go ahead and erase my prime factoring over here, except we're going to remember that our least common multiple is 2 squared times 3 squared times 5. So we put this up here. LCM is 2 squared times 3 squared times 5. 4 times 9 is 36 times 5 is 180. Now let's go ahead and look at how we have written this, compare our factored denominator to our least common multiple, and see what factors are missing here. When we look at 50, we see we have 2 squared times 3 times 5. Our least common multiple is 2 squared. We have a 2 squared. It's 3 squared. We only have one factor of 3. And it's 5. We have the factor of 5. So, if you will, we have our factor of 2 squared. We have our factor of 5. But our least common multiple requires 2 factors of 3. And we only have 1. So what is missing? Well, we're missing an additional factor of 3. So that is what we're going to have to multiply this first fraction by 3 over 3, because when we multiply with a 3 in the denominator, we end up with our least common multiple. Now let's go ahead and look over here and see how our denominator compares to our least common multiple. And sure enough, 3 squared we have, 5 we have, but we have a problem with our factor of 2. Here we only have one factor of 2. In our least common multiple we have to have 2. So what is missing here? We're missing a factor of 2. So we're going to multiply the first fraction by 3 over 3, the second fraction by 2 over 2. And we do that because as long as you multiply any expression by any number by 1, you don't change its value. We have 21 over 180 plus 22 over 180. You add that together and you have 43 over 180 is the sum of these two fractions. And it's this procedure right here that we're going to use when we find common denominators for rational expressions. And that common denominator is the least common multiple of two polynomials. So this is what we say. It says to find the least common multiple of two or more polynomials, first you factor each polynomial completely. And that's what we did, where I showed you the prime factorization of 60 and the prime factorization of 90. Then the second step in finding the least common multiple of two polynomials is to find the product of the highest power of each factor. And that's a mouthful, but all that is exactly what we did here with these fractions. We found the product of the highest power of each factor to get our least common multiple, and then we added our missing factors to come up with the common denominator of 180. Okay? So all of this was actually a really good review of how you find a common denominator, just fractions. But let's go ahead and move this on into rational expressions, which include variables in them, can include polynomials in them. Okay, first we're just going to find the least common multiple of two polynomials without even turning them into rational expressions. And this is example 1, and I'm on page 495. It says find the LCM of x to the fourth minus 3x cubed minus 10x squared and 3x squared minus 30x plus 75. Go back and make sure you've copied your problem correctly. X to the fourth minus 3x cubed minus 10x squared. 3x squared minus 30x plus 75. So we're all right with those. What do our instructions here say? Factor each polynomial completely. Two polynomials, we want to factor them completely. What's the first thing that we are going to do? We're going to check and see if there is a common monomial factor. So when we look at this, you see that there's a factor of x squared in common. Factor out the x squared. What do we have remaining? X to the fourth divided by x squared is x squared. X squared times x squared, x to the fourth, minus 3x minus 10. This should be very easily understood by you, that we have a common factor of x squared. Now we have a we have a trinomial in parentheses that will factor into two binomials. We've been factoring trinomials for a very long time now. And if you're not able to look at this problem, and maybe not so quickly as I just did, but if you can't look at this and see that this trinomial factors into x minus 5 times x plus 3, go back and review how to factor trinomials, because this is a very basic trinomial that you're factoring, and you need to know how to do this. So we see that we have these expressions here. We have a factor of x squared, factor of x minus 5, and a factor of x plus 3. So let's see what our second trinomial factors into, and we have 3x squared minus 3x plus 75. There's no common variable here, but we do have a factor of 3 in common. When we remove that 3, we have 3 times the quantity x squared minus 10x plus, not 75, but plus 25. So when you're working these problems, be thinking as you're working and make certain that you factor your common monomial factor out of every single term. A good way to catch the error before you keep it in your problem is say, okay, 3 times x squared is 3x squared. 3 times a negative 10x is negative 30x. 3 times 25 is 75. If I'd kept if I'd left that as a 75 and taken the time to go back and say 3 times 75, oh, I forgot to factor out the 3. Take your time. Now this, you could look at and say, okay, that's x minus 5 times x minus 5. But remember we studied some special products. We talked about perfect square trinomials. We talked about the difference of two squares. This right here fits the pattern of the difference of two squares. The first term is squared, x quantity squared. The second term is the third term is a perfect square, 5 times 5. And the coefficient of the middle term is twice the product of the square roots of the first term. Square root of the first term is x. Square root of the third term is 5x. Twice that product is 10x with the negative sign. So this tells you the pattern that you have 3 times x minus 5 used as a factor twice. If you don't recognize that that's a perfect square trinomial, that's all right. Just factor it out. But then change your factorization to incorporate exponents, because they want you to remember you factor each completely and then you find the product of the highest power of each factor. You don't want to be repeating factors. You want to reuse this in exponential notation. So now, what is our least common multiple going to be? It's going to be the highest power of each factor. What factors do we have? We have a factor of 3. We have a factor of x, only occurring once, so we use its power here, x squared, 3 times x squared. We have a factor of x plus 3 in parentheses, and we have a factor of x minus 5. This factor of x minus 5 occurs in the factorization of both of these expressions, but it's used twice here. So our least common multiple includes 2 factors of x minus 5. And you would write the least common multiple without the raised dots. It would be 3x squared times the quantity x plus 3 times the quantity x minus 5 squared. Really strange looking common multiple if you're used to thinking of common multiples as only being with fractions. But this is following that same procedure. This is what we're going to be using to come up with a common denominator when we are dealing with rational expressions. So let's go ahead and do now example number 2, where we actually find a common denominator of a couple of rational expressions. And we're going to see this. We're still on page 495. And we want to add 3 over 2a plus 5 over 8a. 3 over 2a plus 5 over 8a, or 8a squared. Let me see. Okay? We want to add these 2 rational expressions together, and you probably already know that our common denominator is going to be 8a. But let's go ahead and use the methodology that says factor each denominator. 2a is 2 times a, 8a is 2 cubed times a, and our least common multiple is going to be each unique factor that appears. We have a factor of 2, and a factor of a is going to be the product of each unique factor to the highest power. We have 2 to the first, we have 2 to the third. So we're going to use 2 to the third power times a as our least common multiple, which of course is 8a. Now, if we're going to go ahead and multiply each rational, that's not supposed to be a 2, that's supposed to be a 3. Each rational expression here by the factors that are missing in the denominator. What factors are missing? We have a factor of a, and we have one factor of 2. So we're going to multiply by 2 squared, which of course is 4, plus 5 over 8a. Don't have to do anything there because our common denominator is 8a. 3 times 4 is 12 over 8a plus 5 over 8a, and that's not seeming right to me. Let me just make sure that it is. I mean, it seemed right to me, it didn't seem like the number that I remembered from the problem. We have a common denominator of 8a. You add the numerators together. 12 plus 5 is equal to 17. And that's all we've done here. Do you have to write it right here where you use 2 squared instead of saying 4? No, but I'm using it this way to illustrate the methodology that will always work. If I were doing this myself, I wouldn't say I was multiplying it by 2 squared. I'd say multiplying it by 4. But you'll see before the end of the video is completed why I want you to understand this process that we're using here. Let's go ahead and use example number 3 now. And that's on the next page in our text, which is page 496. And on page 496 we have example 3, which says simplify 2x minus 5 over 3x plus x minus 1 over 2x plus 5x plus 6 over 12x squared. Make sure we have the right thing. 2x minus 5, 3x. X minus 1, 2x. 5x plus 6, 12x squared. How do we find our common multiple of this? You can look at this and you see again, probably half of you, that our common multiple, or our common denominator, is going to be 12x squared. But let's go ahead and step through the methodology. We're going to write each denominator in factored form using exponents. 3x is 3 times x, 2x is 2 times x. The prime factorization of 12, 2 squared times 3 times x squared. So we show the prime factored form of each denominator. Now how do we find the LCM? The LCM is equal to each unique factor that appears in any of these expressions. So we have a factor of 2, we have a factor of 3, and we have a factor of x. And least common multiple is always written as a product. Now, it's not enough to just say we have a factor of 2, but we're going to use whatever the highest exponent is, or the highest power. 2 to the first, 2 to the second. Obviously, it's 2 to the second. The highest power of 3, 3 to the first, both places. The highest power of x, first, second. It's x squared. So, our least common multiple, as I stated earlier, is 12x squared. So now, let's go ahead and see what we're going to have to multiply each of these expressions by so that we end up with a common denominator. Let me erase our work here. We have 2x minus 5 over 3x. Let me rewrite our common denominator, or our LCM. LCM is 2 squared times 3 times x squared. What factors are we missing here? Well, we're missing a factor of 2 squared, and we're missing a factor of x. 2 squared times x. Everybody agree with that? What about in our next term? We have x minus 1 over 2x. What factor are we missing? Well, we're missing one factor of x, we're missing a factor of 2, and we're missing a factor of 3. Missing a factor of 2, missing a factor of 3, missing a factor of x. 2 times 3 times x. And for our third term, the 12x squared is our common denominator, so we're not missing any factors. Plus 5x plus 6, all of this over 12x squared. I wrote it so that you would see the concept of using prime factorization and using powers of each factor to help you pick out what's missing. Let's go ahead and change this a little bit, and as I do, I'm going to change the order of multiplication here. Track with me. 2 squared is 4x over 4x times 2x minus 5 over 3x. Two squared is 4x over 4x. We're just multiplying this rational expression here by a value that's equal to 1. I've moved this into before our original rational expression here because we're going to have to multiply that binomial. And I want you to notice, matter of fact, I'm going to add these in green. I want you to notice that I added parentheses in here because you are multiplying the entire product. You're not just saying 4x times 2x. You're multiplying, you're multiplying this entire factor here, 2x minus 5, to get your resulting product. Now, what do we have? We have 2 times 3 is 6 times x, so you have 6x over 6x times x minus 1 over 2x. And once again, I'm going to enclose the x minus 1 in parentheses. The reason I'm doing that is because we're multiplying that entire binomial. We're multiplying x minus 1 times 6x. And then we have our final third term over here. Plus 5x plus 6 over 12x squared. What do we do next? We multiply. 4x times 2x, 8x squared. 4x times a negative 5, negative 20x. All of this over 4 times 3 is 12x squared. Everyone make sure that you understand what I have done here. 6x times the quantity x minus 1, 6x times x is 6x squared. 6x times a negative 1 is minus 6x over 12x squared. Plus 5x plus 6 over 12x squared. So our problem is getting a little bit lengthy here. But now we have ended up with a common denominator. When you have the same denominator, how do you come up with your solution? You add the numerators. So for our answer here, we're going to have a denominator of 12x squared. We're going to add our common terms. We have 8x squared plus 6x squared gives us 14x squared. Now we're going to combine our x's. Negative 20x minus 6x is, negative 20x minus 6x is, let me look in here to see if I did something wrong. Negative 20, got a negative 20x minus 6x should be a negative 26x plus 5x is a negative 21x. Everybody tracking with me on that? What do we have here? Still remaining, we have a factor of 6. Plus 6. All of this is going to be over 12x squared. (14x squared minus 21x plus 6, all over 12x squared. Is there anything that we can reduce? Do they have any common factors? No common factor of 2. No common factor of 3. This solution right here, this rational expression right here, is the solution to our original problem. 2x minus 5 over 3x plus x minus 1 over 2x plus 5x plus 6 over 12x squared. You see that there's rather a lengthy process involved. Do not get in a hurry trying to do these problems, and don't think that you can sit down in front of your iPad with your iPod in, playing a video game with somebody, texting back and forth with 5 people at the same time, and being on Facebook and Twitter. You can't do it. You've got to have your concentration here so that you can go through and make sure that you're not dropping anything. Okay? I want to go ahead and do one more example from your homework. I realize this video is getting lengthy. I also realize that we're at the end of the year and some of you guys have checked out already. You really don't want to, you might want to check out, but it's not wise because we're pulling a whole bunch of stuff that you've been learning all year, pulling it all together to be able to truly do some calculations here in Algebra 1. Let me go ahead and pick, oh my, which one did I say I was going to do? I'm going to do example 9 on page 496. Problem number 9, rather, on page 496. And this says we want to add 3x over 9y to 4x squared over 6y cubed. First thing that you want to do before you're going to come up with a common denominator is look and see if these expressions are reduced to lowest terms, and they're not. 3 over x divided by 9 over x, they have a factor of 3 in common. So we're going to take care of this first and rewrite 3x over 9y as x over 3y. And then we have a factor of 2 in common. So our second term becomes 2x squared over 3y squared. Have to see what we need for our common denominator. Our first denominator is 3 times y. Our second denominator is 3 times y squared. What's our least common multiple? It's the product of all of the denominators the highest power, did you hear what I said? The product of all of the denominators, product of all of the factors of all of the denominators, the highest power that's used. So our least common multiple is 3y squared. 3y squared is our least common multiple. We're missing one factor of y. So we're going to multiply the first term by y over y so that we end up with both of these expressions having the same denominator. So we have xy over 3y squared plus 2x squared over 3y squared. Denominators are the same. We're going to add the exponents together. So the denominators are the same. 3y squared, we add the exponents together. xy plus 2x squared. This expression does not reduce. We do have a common factor of x in the numerator. So technically, you could write this as x times the quantity y plus 2x. All of this over 3y squared. But it's not necessary because you have no common factors that you cancel out. Would I accept this answer or this answer? Absolutely. Your book is happy for you to leave your solution in this form because there's no further cancellation of common factors for you to carry out. That's the end of section 12.5. Take your time working on these. I know you can do a good job. I'll see you next time.